So in this video, I'm going to be showing you how to derive the expression to find the maximum angular frequency you can rotate a cup on a turntable without the water spilling up over the sides. So to kind of help us think about this, I'm going to draw a couple pictures on the board and kind of explain as I go. So we have our cup of water before we spin it, and it has some initial height of fluid. I'm going to call that H naught. The cup also has a radius of R. I'm going to call that big R. And then there's the overall cup height, and I'm going to call that big H. And then once we spin the cup, so give it a little spin, it's going to look something like this. So trying to kind of get these close to each other. The water is going to kind of bow out like this. So I drew it a little bit exaggerated, might not dip this much, but it'll kind of help us see what's happening. So we're going to have kind of some depression from the initial height, called D, and then there's also kind of this unchanged area down here. Right, and so we are to find the expression for the maximum angular frequency. We're going to first find an expression for these two variables D and also H, which is the height of the fluid at any point moving away from the radius. And then using this, we'll be able to find our expression. So I'm actually going to start by finding an expression for H in terms of values we know. And so I'm going to start with the static fluid equation, which is the change in pressure with respect to a change in distance equals rho times acceleration. So in this problem, since we're spinning the cup, we're going to have centripetal acceleration. So A is going to equal omega squared R. And we're also going to have a change in the radius, not a change in distance. So instead of changing with respect to Z, it'll be with respect to R. So our new fluid statics equation for this specific problem is this. So we have our change in pressure with respect to the change in radius equals rho omega squared times R. So from here, we can separate our variables and integrate. So on the left side, we're just left with dP. On the right side, we have rho omega squared R dr. Now we integrate both sides and set our bounds of integration. So our initial point is going to be this center of the radius. So the pressure here is just atmospheric pressure since there's no water above this point. I'm going to call that P1. And then to some new pressure over here, which is P. And then same thing, our starting point is the middle, R1, to some other point, R out here. So this distance of R. So now we can integrate. Integration of this is just going to be P minus P1 equals the integration of R is just 1/2 R squared. So we're going to have our constants out front again. And we're going to have 1/2 R squared minus 1/2 R1 squared. So like I said, our starting points are going to be equal to, or going to indicate the values at the middle of the cup. So our starting pressure is atmospheric pressure. Since we're kind of considering this in gauge pressure, atmospheric pressure is 0. Because we're more focused on the change in pressure, not the absolute pressure. And then for the radius, since we're starting at the center, R1 is just also going to be 0. So we're left with this expression over here. Our pressure equals rho times omega squared times R squared over 2. So this is one way to kind of model the pressure as we move out from this area, or from out from the center, the pressure of this liquid against the side of the cup. Another way to do it is just using the buoyancy equation. So that equation is just the pressure equals rho GH, and in this case, H is this distance here. So now we can set these two equal to each other and solve for H. So in this case, the rho terms cancel, and then we just have to divide by G. And so our equation for the height is omega squared times r squared over 2G. And so now we have an expression for the height. Next, we need to get an expression for the depression, D. So I'm going to write this over off to the side. We'll use it later and kind of erase the board. So now we used pressure to get an expression for H. Now we're going to use volume to get the expression for D. And we're using volume because it's going to kind of remain constant from here to here because none of the water is spilling outside of the cup. So the volume in this area of the cup is going to equal the volume in kind of this area of the cup that's been squished up against the sides. And so the first way to express this is just the easier way. It's just going to be the cross-sectional area of the bottom cup times the height. So the cross-sectional area is just pi r squared, and then the height of this section is just D, our depression. Now, the second way we're going to kind of model this height is we're going to think about it a little bit differently and kind of take a look at a top-down view and kind of take a sliver of the radius here. And then if we add up all of these kind of little slivers of volume around the cup, that'll give us our total volume. So this differential change in the radius, I'm just going to call dr. And kind of that same way we did this, we need the area times the height. And so for this, the differential area is just going to be the circumference, which is 2 pi r, times our width, dr. And then to get the volume, we just have to multiply by height. And so we actually have height in this case, and it is h. So dv equals 2 pi r h dr. And so now we can set these two equations equal to each other. I'm going to erase my drawing here. And we'll integrate this side and then solve for d. So we have pi r squared d equals 2 pi. These are constants. R, I'm going to plug in our expression for h here, which is just omega squared r squared over 2g. And we need to integrate this with respect to dr. So now we can pull out our constants, which is this 2 pi, omega, and 2g. And then left in our integral is just r times r squared, which is r cubed dr. Taking a look at this, you can see that some of the terms are going to cancel. So these 2's are obviously going to cancel. And then we have pi on both sides, which is going to cancel. And now before we integrate, we need to set the bounds. So same idea. We are kind of adding up these volumes from the middle of the cup. So our radius is going to be 0 to the outside of the cup. So radius of big R. Now we can integrate. So the left side of the equation is unchanged. Our constants left are just omega squared over g. And then if we take the integral of r cubed, it's just 1/4 r to the 4th. So we have 1/4 big R to the 4th minus 1/4 0 to the 4th. And so this term is just 0. So we're left with just this expression for the right side. Now we can cancel out this r squared with this r/4, or r to the 4th power. It'll just become r squared. And that is our expression for D. So our depression equals the angular frequency squared times r squared over 4g. And again, I'm going to write it off to the side. And now we can go and get at our expression for the maximum angular frequency we can spin the cup. So our next step is to kind of use the overall height of the cup and basically set it equal to this maximum height of the liquid. And so how we're going to do that is we have our big H equals the unchanged distance here, kind of at the bottom of the cup. And we can get at that by the initial height of the liquid minus our depression, which will leave this sliver down here. And then we also have the rest of the height above the unchanged area, kind of above the lowest point. And so that is just going to be our H max, or H at big R, right? Because the fluid is going to be all the way up to the top of the cup without spilling over. So we have the height here and the height here, and that is going to equal the total height of the cup. Now what's left is to just plug in our values for H and D and solve for the angular frequency. So I'm just going to plug in those values. Equation for D is omega squared big R squared over 4G plus H at big R. So it's just going to be omega squared, plug in R for R squared, or plug in big R for R, you get big R squared over 2G. So now these terms are actually very similar. We're left with basically 1/4 times this term plus 1/2 times this term. This is negative, so 1/2 minus 1/4 is just 1/4. And so we're left with omega squared big R squared over 4G. So H naught plus omega squared times big R squared over 4G equals the total height of the cup. Now we just solve for our angular frequency. So we can subtract H naught to the left side of the equation. We have H minus H naught, and we're left with omega squared R squared over 4G. To get omega squared alone, we need to multiply by 4G. And then divide by big R squared. And all that's left is to take the square root of both sides of the equation and rewrite our expression. So omega, the maximum, or the angular frequency we can spin the cup without water spilling over, is going to be equal to 2 times the square root of G times H minus H naught over R. So this is the expression for the maximum angular frequency. We can spin the cup without any water kind of dumping over the side.